Streaming is now turned on. Give it a few seconds to refresh on the YouTube side. And we are now ready to start the class. All right. So what you're seeing here is kind of my Design Hub documents, which are definitely not related to our class today. All right, so this is back to our class. And as some of you can see, I put up a space folding picture in Discord today. Now, obviously, this is not a physics class, not even a theoretical, physics class, obviously. But what we're going to do today is to space fold, which is a continuation of what we talked about last Thursday. And I checked my own video just today. Just the last portion of the lecture on last Thursday. And I think I quite explicitly said that it is important to review the material and definitely finish up, the Aleph Null module today. And also, if possible, read the relations module. In other words, okay. Okay, go ahead, Alex. Yeah. Go ahead. Oh, okay. So that's kind of my expectation. I'm expecting people to have done all that. And if people are thinking, are you seriously expecting, students to read over a long weekend, of the material that was taught in the previous week? The answer is yes, I do. So that hopefully that clear up some of the potential questions that somebody may have in their mind. So with that, we're going to continue with our discussion. So there's a lot of math involved in all of this. I wouldn't say a lot of math. It really has to do with how this math is related to the derivation. In other words, I'm not trying to only teach the knowledge that you need to know, but also, how I, reason out these things, because a lot of these derivations are not canned derivation that I copy from somewhere on the internet. These are pretty much, all of my own derivations. And as I go through these, steps, this is how I solve a problem. Okay, this is how I derive an answer. So I'm hoping that some of this, will be helpful, because I want to illustrate at least how I think, which may or may not be how you think or how you want to think. Okay, so there are several variables here. But I think, this is all useful when it comes to being successful in computer science. Okay, not necessarily computer program development, because development is a separate thing compared to computer science or computer engineering. I'm looking at the text channel here. Does anyone understand the differences between a developer compared to a software engineer, and comparing that also to a computer scientist? So I just want you guys to kind of ponder upon that just a little bit, because I think it is important to understand the differences. Okay, all right. So Aaron said, so between soft and engineer, not quite sure to what you're referring to. All right, so I'm just gonna type it up here. Okay, right. Okay, so I'm gonna give you guys an analogy, which I hope is useful. But this is basically how I look at these classifications, which may or may not reflect, okay, what industry does. But I was part of industry once, so I was part of the people who define these terms. Okay, okay. So I'm just gonna put terms over here, and then the first thing I want to do is to define what is a developer. Okay. So in the world of actual construction, a developer is more or less what we call contractors. Okay. So these are the people who go to a job site with tools, okay, with supplies. They are the ones who bring along the 2x4s, the 4x4s, sheets of wood, hammers, nails, and so on. And these are the actual people who finish up a house. Okay, so when you look at the people who touch, to actually get the house, done, these are the people who actually, quote unquote, get it done. Okay, so these are the developers. So now we move on to software engineers. So software engineer is somewhat a combination of two jobs related to how to make an actual physical house. So a software engineer would sometimes serve as an architect. Okay, architect, I think that is correct spelling. Yep. Okay, but at the same time, the software engineer will also act as a civil engineer. So these two types of people in the context of constructing an actual house. Okay, where's my quote? There we go. So these two people, these two types of people in the context of making a house. The first one, the architect, would I think that's looks like a typo, but I cannot find that is a typo. Architecture. So I think that's the right one. Anyway. So an architect is the one that would look at the client's needs, okay, and look at what the client wants the house to do to come up with a design. So if the client says, I want to get a really good ocean view because I spend a lot of money on this lot of land, I want a great ocean view. So the architect will probably ask the client and ask, okay, I can give you a deck. Okay, which part of the house do you want to face the ocean? Because a house can only be only one side of the house can face the ocean, right? But if the client seems, quote unquote, unreasonable and say, but I want every single side of the house to see the ocean, then the architect would go like, that is difficult to do, but I think we can do this by using a whole lot of, guess what? Mirrors, right? But that's the job of the architect, okay, is to find out what how a design can be done to meet all the requirements. But an architect has no knowledge of civil engineering topics like what kind of a foundation is needed, okay, what is the load factor, what does the grade of the land or of the lot has to do with how whether such a house can be constructed and whatnot. In other words, an architect does not actually look at the pragmatic consideration of whether it can be done, okay, or can be done safely. It does. An architect may not look into safety requirements. Okay, that is the job of a civil engineer. Okay, so once an architect is done with a overall design, a blueprint, dimensions and whatnot, a civil engineer would then come in and look at it and go like, this is not doable. Okay, we do not have any type of material that can accomplish this. Okay. Or these mirrors, the way you configure these mirrors would just be blown away, when we have 50-mile-per-hour gusts. Okay, so the civil engineer is the one who comes in and say, nah, cannot be done, nah, cannot be done. Or if you want this to be done, okay, you will need your high-strength steel. You cannot just use your regular steel, okay? Or you need a special kind of concrete, to get this done. The civil engineer may look at this and go like, because of the temperature variation of where the house is going to be, okay, if you want this house to be safe, you have to use this kind of material because of the expansion and contraction just due to the daily change of temperature and so on. So the civil engineer is doing that, but both of these roles are combined in what we call software engineers in the computer programming field. So now we have computer scientists. Okay, so computer scientists, in this context, in the context of constructing a physical house, they are the actual scientists. Okay, so they are the actual scientists. So they are the chemists, they are the physicists, and so on. So these are the actual people who would look at physics, okay, and discover new laws of physics. These are the people who would derive the equations in physics, so that the civil engineers can use it. So in computer science, okay, CISP440 is definitely more leaning on the quote-unquote computer scientist side than the other two. Software engineering, I don't think we have any classes focusing on just that. But CISP430, okay, data structure, is kind of more leaning on the software engineering side compared to the developer side. The developer side is really just, okay, given the tools, which are your programming languages, right? How do you use these tools to write a program? So when it gets down to the developer side, it all has to do with the API, the application programming interface, the programming language itself, the syntax, the tools, which include the IDE, the integrated development environment, has to do with the debuggers. Okay, it has to do with what operating system you're using, what kind of platform you're using in general. Are you using Google's platform, or are you using some other platform? So that is kind of the separation between the three. You can probably also kind of imagine the pay rate, within these three, and as well as the proportion of people in the workforce for these three. Developers, there are plenty of developers. There are a lot of developers because we need a lot of people to actually, to write the software, because writing software, even now with all the tools that we have, is a really kind of tedious process. Mostly it has to do with debugging, okay, because everybody puts in a bug and then now we have to fix the bugs. Okay, fixing bugs is what is taking a lot of time. Software engineers, we don't need as many, because these are the people who are actually doing the design. Now it doesn't say, this is not saying that software engineers cannot code, okay, that is not the case. A lot of software engineers would also code at the same time, so they would sometimes take on the role of developers. But in terms of qualification, they are two different types of qualification. I would say software engineers are more demanding when it comes to qualification. And then when we move up to computer scientists, those are the positions for computer scientists are even more rare because they are not quote-unquote needed as much. Okay. So now here comes the fun part. Okay, the fun part is, what about hackers? Okay, I don't really care whether it's black hat, gray hat, or white hat. Okay, where do hackers fit into this picture? Hackers are the thieves trying to break into a house. Okay, that's basically how hackers fit into this whole picture. Now, whether it is a security expert hired by a billionaire and say, okay, I want you to check all my security settings to see whether my house is susceptible to theft, and some invasion, or to all kinds of threats that can happen, that would make the consultant a white hat. Or it can be a black hat, okay, an actual thief, an actual robber. But those are the hackers. Hackers are trying to circumvent things to get to a resource that the hacker is not supposed to get to, right? So hackers actually interestingly cross all three of these levels. In other words, some hackers, if a hacker is only at a developer level, then that particular hacker can only utilize existing methods, existing tools in order to do the hacking. In other words, that hacker is basically looking at somebody else's crime and just say, I can copy that. Okay, but that would not make the hacker very successful, because if a crime has already been committed and publicized and known, okay, most people would have closed those security loopholes already. So the next level are the software engineers in the hacker world. So these people are the ones who would look into the infrastructural aspect of computer systems and say, okay, if this is the architecture, if this is the system, okay, operating system and whatnot, how do I circumvent all of these things? And at the highest level, you have the computer scientist turned into hackers. So these are the people who will look into crypto theory and go like, I'm not attacking at the program level, okay? I'm not utilizing known exploits of a particular program. I'm not even looking at brute forcing passwords and whatnot, okay? I'm looking into the very fundamental part of computer science. I'm looking into crypto theory to see if a particular crypto algorithm has loopholes, where it is easy to find the other key, okay, if you're using a key pair method, okay. So these are the mathematicians, okay, more or less, they're actual mathematicians. All right, so that's kind of what I want to introduce at this point of time, just so that you guys can understand what these three different types of people are and what role do they play in the world of software stuff, okay? Because you need people who actually write the software, developers. You need people who would design software, the overall architecture, and then you have people who work on the theories of basically everything that has software in it, and those are the computer scientists. Yep. Developers would only make petty thieves, unfortunately, in the world of hacking. The most successful, hackers, tend to be between, the software engineering and the computer science scientist people. Okay, so what this class is about, okay, getting back to this class, all these, Sigma notation and whatnot, this is actually more or less, on the computer scientist level, but it's very entry level to, at that level. Okay, so this is just a taste and exposure for you guys to see what that is involving. So all the reasoning that I'm going through here, it does not benefit, well, I wouldn't say it does not, but it does not benefit as much to people who just want to write some software. Okay, all I want to do is to become a game developer. Well, you don't really need to take a class to do that, okay, because you can just go to a lot of what they call, how do you call those schools where they give you, they take like $20,000 and then they give you like 8 weeks of classes, boot camps. Very good. Yep. So you can take a boot camp and and quote unquote become a game developer. Unfortunately, that will not get you very far. It will get you far enough to get jobs, but your upward mobility may be limited if all you have to show to future employers when you want to apply to a different job is that I have gone through a particular boot camp. A lot of jobs require a 4-year university a bachelor's of science degree. So a boot camp does not give you that. Now, if you already have a Bachelor of Science degree in computer science, and you say I want to specialize in a particular kind of industry job, so I go through a boot camp, that works exceptionally well. But at the same time, a lot of people like that, they usually do not need to use a boot camp, so they use a boot camp only when the certificate of a boot camp is well recognized in industry. Then it is worth the time to go through and pay for the boot camps. All right, very good. Okay, so are there any questions? So getting back to the actual class content now, are there any questions about this particular derivation? All the tricks related, well, I shouldn't say all, but most of the tricks related to this derivation really has to do with breaking down a summation series and just see how we can transform from 1, break it into 2, just like that, with splitting. And then from these 2, we want to unify the indexes, okay? So the indexes of how I changes, within the sigma, we want to unify so that we can recombine the split into 1. So you might say, well, then what is the difference between the original one and the one that is recombined from the split sigmas? The difference has to do with the range of the indexes. The original one range, the range of I in the original series goes from 0 to x, and the modified ones go from 0 to x minus 1 divided by 2, or x divided by 2, the whole thing minus 1, depending on whether x is odd or even. Okay, so that is the difference. But in the process of doing this, we are looking at the term that we are summing over, which originally is an I, which depends on which iteration of the summation we are dealing with. We turn that into a constant as far as the summation is concerned. In other words, we turn this I, okay, over here, into this x over here. Now x is not a constant per se because we are given x, but at the same time x does not depend on I, okay? And as a result, if you have any type of sigma notation where each term that you're summing is just x and it does not depend on I, then you can just say, oh, okay, so we are just adding x plus x plus x plus x plus x. How many times? That has to do with how many times you're going through, quote unquote, the loop, because the summation is really a loop of sorts. So now you can basically say, okay, I can see that in this case, we are going through the sigma notation. There are this many terms in the sigma notation, but each term is only x, and therefore we can just, hey, instead of sigma, we now turn the summation into a multiplication. So that really is the most crucial step of these derivation, is to turn a summation, the sigma, into just a multiplication. Turn a sigma into a plain multiplication. So after that, okay, the last few steps, which is starting from, oops, okay, maybe I should just point out here, from the 5th line from the bottom of the derivation all the way to the last one, it's only about unifying the two cases, because we got one case that deals with when x is odd, we got the other case when x is even. So the idea is, well, we look at those two, and as it turns out, you know, using algebra manipulation, they can be unified into one single one. So if they are the same, no matter whether x is odd or not, then we can just use the unified formula or expression instead of, you know, needing to differentiate whether x is odd or even. So that is the general strategy of this entire derivation. Now you might ask, is that really needed? Because I can just look up the internet and find that this sigma here equals to this term over here. So from the knowledge perspective, that is not needed. Okay, you know, we have just wasted a whole bunch of time to, you know, go through the derivation. But from the other perspective, which is how do we get something derived, then this entire exercise can be useful. Okay, because it really kind of shows, you know, how it is done. And how much do we want to know how something is done, you know, such as how do we go from here to here? It really goes back to this picture over here. Okay, where do you want to be, okay, as a job? Okay, some people enjoy being a developer, okay, just getting things done, because there's a certain gratification when you actually see a game developed. Okay, and you can say, I put in my actual code into this game and I got this done. Okay, and the result is something that is, I would say, as tangible as it gets in the world of software, because you can't really touch software, but you can play with it, you can interact with your software. So there's a certain sense of gratification, you know, being a developer. Software engineers would look at the product and go like, well, I did not contribute a single line of code, but I did the overall architecture of this entire thing, and it works well. Okay, you know, look at this game here. It is so scalable. Whether there are only 5 people, you know, playing in the multiplayer, you know, realm, or whether there are 500, this system scales up without any problems. Okay, you can even scale it up to 50,000, you know, players in the same realm, and it will still run. Okay, you know, you just need to throw more resources at it, because there are certain types of multi-user interaction, you know, method where it does not scale up, and then there are others that can potentially scale up really well. So the software engineer gets the gratification from looking at that aspect, not so much, you know, just playing with the game itself, but to look at how the game can scale up, you know, when there are more resources, or how the game itself, you know, can benefit when there are expensive, you know, GPUs available, so everything looks really nice and cool with all the details. But if you throw an old computer at the game, it is still quote unquote playable. Okay, it's just that you just lose a lot of details. Okay, a lot of the shadows, a lot of the reflections, you know, it's going to be lost, but the game will still be playable. That is another way that a software engineer can feel, you know, happy about the product. The computer scientist, on the other hand, would get the satisfaction from something that is also a little bit different from what the software engineer does, because the computer scientist would get the gratification from, oh, this is something that nobody has done before. Okay, I have just discovered something that is fundamentally new to the gaming world. Okay, I discover a new way to do physics simulation. Okay, that was never done before, and it seems to be a brand new way of getting things done, and I think this is great. So so that really has to do with what we are talking about here. Okay, all right. And you guys are taking this class, which means you're close to transferring to a 4-year university, so you don't even have to make a choice yet, okay, as to where you want to be, when you get out to the world. Most people have to start, as developers, or some people who are, having, depending on what classes they have taken, the focus. Some people can start as software engineers, but almost nobody can start as a computer scientist unless they have a graduate degree, like a master's of science, and most of the time you need a PhD to start as a computer scientist. So, but by the time you graduate or close to graduation with your 4-year bachelor's of science, then you can start to think about those questions. But it doesn't hurt to be aware of those things. All right. So now we have a mechanism to compute. Let me see if the spreadsheet is still around. I rebooted my computer several times, so I may or may not still have the spreadsheet. So let me see if that is the case. All right. I'm just checking this off of the screen that you cannot see. Yeah, so I may not have kept the spreadsheet that I worked on the other day. Okay, well, that's fine. We can always just kind of work it out today. There we go. All right, so remember, X goes across and then Y goes up and down. Okay, so now, if we are to name these cells, this would be 0, 0. It was on the Google Sheet? Oh, okay. If it's on the Google Sheet, then we probably still have it. Because I remember I used, oh, you're right. Okay, excellent. Thank you. Ah, okay. Thank you, Gary. You guys remember things that I do not remember, even though I am the one who did it. Cool. It's kind of like distributed memory, right? All right. That would be a separate topic where I will throw in Ghost in the Shell into the whole discussion. But that's a whole different discussion. We are not going to go there now. Okay, so looking at this thing here, so now we have a way to compute the integer or natural value of everything on the first row, because that's when y is a 0 and x goes from 0, 1, 2, 3, 4, and so on. So we have no problem now computing the value of any one of these particular cells. So now the question is, well, given that, how do we compute the value, the natural number corresponding to a particular cell that is not on row 0 per se? Okay, we see this is row 1, but remember we count from 0, so this is actually technically row 0 from the perspective of the equation. So one thing we can do is to kind of, when we encounter questions like this, the first thing we can do to try to figure it out is to use concrete examples. Okay, I start with concrete examples. I'm not smart enough to skip all the concrete examples and jump directly onto the theoretical derivation. I have to start with concrete examples. Okay, so I can say, well, if I know the value of this particular cell, okay, I'm highlighting the one that on the screen, how do I figure out other things like this one over here or this one over here? So now I want to look at a pattern. Okay, I want to see if there's a particular pattern that I can generalize to help me solve this problem. So we can see that this is 4, 0, 3, 1, 2, 2, 1, 3, 0, 4. I notice two things. Okay, one is particularly helpful to figure out what value that thing should be. And then the second one has to do with, this might come in handy at some point, okay? So let me explain which two observations I'm making. The first one is, hey, look at the y coordinate of these cells. They just go linearly up, okay? 0, 1, 2, 3, and 4. Well, that makes sense, right? Because this is just a staircase, okay? So every step, in terms of the y number, is just one higher than the one quote-unquote before. So 1 is 1 higher than 0, 2 is 1 higher than 1, 3 is 1 higher than 2, and then 4 is 1 higher than 3, and so on. But when you look at the actual natural number that they should be getting, they're also following the same order. The natural number corresponding to this cell is 4 plus 3 plus 2 plus 1, which is 10. This is supposed to be 11. This is supposed to be 12, 13, and 14, right? Oh, so if I know the natural number corresponding to a cell on row 0, I just have to add the y coordinate if I want to figure out the natural number of a cell of that particular diagonal line. So we are talking about diagonal line, meaning the ones which have the same background color in this case. So if I know this has a natural number of 10 corresponding to it, and I want to figure out this one, I just say, okay, just add 3. If this is 10, this is going to be 13. And that's only because I know the y coordinate of this particular cell, which is on the same diagonal line as the base that I know, of which I know the natural number. I just add the y coordinate to the natural number of the one at the base. So that's my first observation, which is really handy to my current problem. But I notice I have a second observation. The second observation is if you add the x and the y coordinate of every cell, of each cell I should say, if you add the x and the y coordinate of each cell along the same diagonal line, they add up to the same value. 4 plus 0 is a 4, 3 plus 1 is a 4, 2 plus 2 is a 4, 1 plus 3 is a 4, 0 plus 4 is also a 4. In other words, if you look at the sum of the x and y, and look at the diagonal lines, every single cell of the same color, they will share the same summation if you just add up the x and the y of that particular cell. Okay, so each diagonal line has a particular summation of x and y. Now, is that going to be helpful for me to figure out the natural number of a particular cell? No, but it is an observation nonetheless. Okay, so it's going to come in handy later. Okay, so do we have any questions? I'm just looking at the text channel to make sure that I'm not ignoring any questions right now. All right, so it looks like we are good. Okay, so assuming that we are good, so now we say, okay, so to figure out the base, the row 0, it's actually not too hard. Okay, we just have to look at the x coordinate, apply that to the closed form equation that we have found here. Okay, so we just say the value is x times x plus 1, the whole thing divided by 2, and that would be the natural number corresponding to that cell. So what we'll do now is to go back to here and say, okay, we'll modify the spreadsheet to also demonstrate what number is corresponding to that cell. So we're just going to concatenate even more stuff to this whole string here. All right, so we'll put a space into the last one, and then we'll put the natural number right after that. So the natural number, which I enclose in text so that we convert a number into a string. Okay, but the number really has to do with just the column number in this case. So it is the column number, minus 1 times the column number minus 1. Now the minus 1 in this case has to do with columns in a spreadsheet start with 1, but we wanted to start with 0, so we have to offset everything by 1, and hence the minus 1. But in the equation, we have x times x plus 1, so we have another plus 1 over here. I know, minus 1 plus 1, why not just kind of cancel out each other? But I want to do it this way because now it emphasizes that column minus 1 is x, okay? So we have x times x plus 1, and that's why I keep the plus 1 and the minus, even though it's after a minus 1, okay? So we have this multiplication, then divide this whole thing by 2. That would give us the value that we are dealing with, and then we press the enter key, and then we refresh all of these cells, okay, just so that we can see whether the equation works or not. Now on anything that is, oh, okay, that doesn't work. No, because it's also copying the formatting of the cells. Okay, well, we have another way to do this. It's just painful. Oh, that doesn't work either because it also wants to copy the equations. Okay, turn off my phone, excuse me. Well, we'll deal with the coloring later on, okay? So we'll go ahead and just copy it, even though it will kind of mess up the coloring scheme, but that's okay. We'll just fix that later, okay? But you can see how we can now compute the natural number value for each cell just using what we have discovered. Okay, let's check whether that works or not. So the way we check is this is 0, this is 1, this is 2, this would be 3. Okay, that works. 4, 5, this would be 6. Yep, that works. 7, 8, 9, this would be 10. Yep, that works. 11, 12, 13, 14, this would be 15. Yep, that works. So what I have done is a very quick verification that using a numerical verification, the equation seems to work. Okay, this is not a real proof that it is working, but it seems to work. Okay, so now the question is, now how do we compute the values of everybody? Okay, well, we just have to integrate the y value into the whole thing. So I go back to square one and I look at this thing here and I say, up to this point, we have the natural number value of a particular cell, but only if the cell has y being 0. Okay, so what we do now is to integrate the value of y, which is I'll put it in parentheses even though it's not really needed. The reason why I put it in parentheses is because this is the actual quote-unquote y coordinate of a particular cell. So the y coordinate in the spreadsheet is known as the row number, but once again we have to offset it by 1 because row 1 has, okay, the row open and close paren would return a value of 1 for row 1, which is the first row, but we call this row 0, in our discussion, so that's why we have to offset it by 1. So we just kind of integrate this part. Okay, this is new compared to what we just did. This is new, and then we go like this, and the first thing we do is we copy this equation over everything on the first row. Okay, and not very surprisingly, nothing changes, right? Because all of these things are on the first row or row 0, and as a result, when you add the y part of the coordinate to the equation, it doesn't add any actual value because y equals to 0 for all of these cells. So now we want to expand it by putting it replicating the equation to all of the other rows. So now we start to see something, right? So let's see if this works. Okay, I know they're all highlighted yellow, which is incorrect, but the idea is we just want to know whether the numbers are correct or not. So now we look at this and go like 0, 1. Oh, this is not good. This is supposed to be 2, so they're off by something. Okay, but let me see how I can debug this, right? So this is supposed to be 2, this is 3, this is supposed to be 4, 5. Okay, so I think I see the pattern. This is 3, and oh, okay, we have to add y to what we are squaring because this guy does not is not in the same diagonal line as this one. it belongs to the diagonal line of this one here. Okay, so that means, you know, I have just forgotten one thing, because the base number is not just based on the x coordinate. It depends on x and y, x plus y. Okay, because x plus y determines which row or which diagonal line we are talking about, and all of them start with, you know, the number that I have just highlighted. So that means, you know, instead of column -1, okay, so let me go back to the first cell to fix it, because once I fix this one and replicate it, then everything would be fixed. So instead of just, you know, x, it should be x plus y. So row number divided -1, and the same thing over here. Okay, so column -1 is x, so we have to add row -1, which is y, and then the +1. Okay, and then this part here is correct. Okay, so we press the enter key, and then we replicate the equation again. Okay, so Gary is typing here, yeah, the starting point of the diagonal is to, yeah, at the corner, right? It's all the way to the first row and all the way to the right. So now we copy this whole thing again, and that seems to look better. All right, so now we look at this and check, okay, does that make sense now? Okay, so we look at the spreadsheet. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yep, so that seems to be working now. So is that okay so far? Does everybody understand how the equation is working? I mean, this is just matching the derivation that I have already explained in the notes. Okay, so in the notes here, the general value of a cell is x plus y times x plus y plus 1, because x plus y is the sum that defines the diagonal line. It counts the diagonal line, and then that whole thing divided by 2. So this portion of the number, you know, if you ignore the plus y, just this portion here, that is the natural number value corresponding to the base of a diagonal line, or row 0, you know, as we know it. But we have to add y to it. So the what we know as x over here is column -1. What we know as y here is row -1, and that basically just translates into the expression or the formula inside each cell. So are we still doing okay? Because what I have just done is to translate what is already in the module, the formulae in the module, into a form in the spreadsheet, so that we can easily visualize, you know, how the numbers get computed. All right, very good. Okay, yeah, I can share the spreadsheet, you know, that's fine. I can do this. Give me a second to share this. So let me give it a name. We'll call this space folding. Okay, and then I will share it to the folder where you guys can see. So I'm gonna move it. Okay, so move to the shared folder. So let me go back up, down to shared. And I don't think I have constructed a whole lot of subfolders here, so you kind of have to dig through. Okay, you know, so just look for space folding in the shared folder. So now everybody can see it. So let me go back to the module. Yeah, you're welcome. But I do want to show people, you know, where to find it in the module. So this is the Canvas website, and if let me switch to student view first, so this way my display matches yours. Okay, see the share folder, you know, which is at the very top, you know, the top module. So if you click on share folder, it goes to a particular folder that I have set up to be shared to everybody in the district. So now you just look for the one that I have constructed, which is space folding. So space folding is right here, and if you double click it, it will be exactly the same spreadsheet that I have been working on. So this way, you can make a copy of this, okay, because you only got view permission to this particular spreadsheet, but you can make a copy of it. Okay, so once you make a copy of it, you can start to annotate it, you can start to modify it, you can start to do whatever you want to to that thing. Okay, so that's up to you to decide how you want to play with it. Alrighty, so getting back to the module over here. All right, so what we have accomplished, okay, what G is actually doing is it is folding. Okay, let me go to here, and that parenthesis is extra. This one is extra. I cannot stand this. Okay, so I'm gonna go fix it first. And I can even share with you how this is fixed. Okay, not that most of you are interested in this, but since I'm doing it anyway, might as well show you how it is done. So this is module 293, and the actual content is module content. So I just have to look for the words that are close to it, which is significance of function. Okay, so we look for significance of function. Nope, just significance of. So it depends on how I wrap the line. So right here, it is the line wrapping breaks it up. That's okay. So we just have to look for the close parenthesis that is not needed, which is this one here. Get rid of it, save the file, and publish it again. So it is just publish. I wrote a script to do all this stuff here. Nope, that is not it. Oh, right, because I have to supply a name. So that would be module.latex. So this just runs all the necessary tools to create the HTML file out of the LaTeX file and upload it to the server. And as a result, when we update here on the server, now if you want to make sure that you are actually updating it, I find that Control R sometimes doesn't really get the job done, or F5 doesn't get the job done. But if you type Control Shift R, that will for sure refresh everything. Because I found that sometimes if I just do a Control R, it does not refresh, because the browser has its own cache, and sometimes without any setting from the HTML document, the browser would go like, hey, but this document is supposed to be good for this long. Even if I type refresh, it will ignore that and go like, nope, I'm not going to refresh. There we go. Okay, so now getting back to our discussion. Okay, so what G is doing, what this particular function G is doing, is it is using n Cartesian product with n as our domain, and is mapping it to n again, which is our codomain. So it is taking a two-dimensional space. Okay, let me show the spreadsheet again, because I think the spreadsheet is really nice to see, because now we can see we can see it both as a two-dimensional space, because if you look at the block that is highlighted right now, it's definitely two-dimensional. Okay, but we can also see the single-dimensional thing, even though it's harder to see, because we can see there's 0, 1, 2, 3, 4, 5. So those are the natural numbers, and we can now sort of see how a two-dimensional space, which is what you can see here as a block, is now translated into natural numbers, right? Because we got all the natural numbers. If we just kind of keep scanning the diagonal lines, we get all the natural numbers. Okay, so we can kind of visually see how we are folding, okay, a two-dimensional space into a one-dimensional space. Okay, now if someone is saying, oh, this is really cool, can we apply this to real numbers? The answer is no. Okay, the problem with real numbers has to do with between any two real numbers, there's an infinite number of real numbers between any two real numbers. That is, well, I should say two different real numbers. Okay, and that's the differentiation between this class and many of the math classes that you have taken, whether it's linear algebra or calculus, or many of the other math classes. Because in this class we deal with what is quote unquote discrete, where we can say we can definitely count elements. We can enumerate, elements in a set, as opposed to in calculus when you're dealing with a real number set. There's no way to quote unquote enumerate. You cannot list the values one by one and go like, okay, see, this is one, this is the next one, this is the next one. There is no next one in a real number, because between any number and what you think is the next one is an infinite number of elements. There's an infinite number of elements between a number and something that is different from it in a real number set. Okay, but in a natural number set or integer number set, if you pick 5 and then you pick 6, I will have to say there's nothing between 5 and 6 that are different, that's different from 5 or 6. Okay, that's just the way it is. Okay, so we're dealing with issues or problems that are more like that compared to calculus and linear algebra, which deal with continuous space, of using real numbers. And complex numbers really can be seen as a two-dimensional real number, because you just get two components and each one is a real number. So it really has the same issues, as a real number space, except it's two-dimensional. There we go. All right. So getting back to the module, okay? So now we want to say, is this, so we want to look at this, g, function g, and the first question is, what about injection, surjection, and bijection? How do those terms apply to this particular g? In other words, if I have two different cells, are they guaranteed to have a different natural number? Okay, that's the first question. That's an injection question, right? Because injection is asking, are things in the domain mapped to not only one and only one thing in the codomain, but we also want uniqueness. Okay, but knowing that we are scanning diagonal lines, kind of like this, it is intuitive in this case to understand that, yep, we are pretty sure this is injective. Okay, give me two different cells, they're going to have two different natural numbers. There's no way we are mapping two different cells into one single natural number, just because of the mechanism. Okay, the very manual method of assigning numbers makes it kind of intuitive. Now, can I count it as a formal proof? The answer is no. Okay, you cannot count that as a formal proof, but I think, just from the intuitive perspective, it is okay to convince ourselves that the function is injective at this point. Okay, so later on we might get into more formal proofs that this particular function is in fact injective, but we'll deal with that later. Okay, so for now we just want to be, we are somewhat convinced that this is injective. What about surjection? In other words, are we mapping to everything in the codomain? That is the next question. So what do you guys think? I can rephrase that question. Okay, if I just give you any natural number, okay, 6031, okay, is there a cell in the spreadsheet mapping to it? Okay, and I think it's intuitive, right? If I just give you one, natural number, no matter how big it is, no matter how horrendous it looks, okay, you can always say, Jack, if we make this spreadsheet big enough, we'll find it, right? So once again, we are intuitively, understanding that it is also surjective, okay? But is it a formal proof? The answer is no. This is not a formal proof, okay? So we'll work with formal proofs of injection and surjection a little bit later, okay? But right now, we are going back and focusing on, yep, we are fairly convinced that it is both injective and surjective, right? So, and we also know that, if it is both injective and surjective, we call it bijective, okay? Or the function itself is known as a bijection, okay? Now, we like bijections, don't we? Because bijection suggests a few things. The first thing in this context, okay, knowing that G is a bijection, is we can now conclude that this set, n Cartesian product with n, has the same cardinality as this particular set here, which is just n all by itself. They have the same cardinality. How do we call this cardinality? It is known as Aleph null. So now we know the set, okay, the Cartesian product of natural number and natural number also has a cardinality known as Aleph null. It has an infinite number of elements, but it is countable. Okay, and better yet, okay, if you just say that, okay, we know the cardinality of n Cartesian product with n is Aleph null, that by itself is just like, okay, what is special about it? What is really kind of special about it is the first part of this equation, which is the cardinality of n cross n is actually the same as the cardinality of n itself. Okay, now I find it kind of cool, okay, even after teaching this class, many semesters, I still find this really kind of cool because it defies intuition, okay, that you can fold a two-dimensional space into a one-dimensional space, quote unquote, without losing anything, okay, because that's the whole point. It is not losing anything, okay. So that's the first thing that we can conclude, knowing that G is a bijection, is it has the same cardinality as the set of natural numbers, okay. That's the first thing. But the second thing that is also kind of cool is with a bijection, we know there has to be an inverse function, right? So the inverse function, I'm just taking a glance at the time. So the inverse function is also interesting because what that means is if I give you a insanely large number, okay, 30,610,000, okay, we can find out what cell it maps to that natural number, okay? There has to be a function that can do that. Does that make sense? Okay, any bijection, has an inverse. So now the question is, how do we find the closed form of that inverse function? Now, I want to emphasize closed form because somebody can say, oh, if you just want to reverse the process, let's say we're given a large number, okay, let's say, okay, relatively large, not really large. So let's say we're given 512, okay, 512 is kind of easy to remember because it is a power of 2, okay. So how do we find the coordinate of a cell in two-dimensional space that maps to the natural number of 512? So the easiest thing we can think of, okay, is really just to say, let's make this table bigger, okay? So I'm gonna do exactly that because I want to illustrate, one way of answering this question, right? So we will just make it bigger. So we'll extend vertically first, and then I mean, you can tell from the numbers that we are getting pretty close to 512. So if I extend it one more time this way, I think 512 is here somewhere, okay? So let's go look for it. Okay, so we can always just kind of use a search function too, but okay, 7, 6, 5, oh, okay, 3 and then 2. So I need to expand this by 2 more columns, then we'll get it, okay? So we say this way, 1, 2, a few more cells doesn't hurt, right? I mean, okay, 512, 513, 512, right there. Okay, wow, nice. Okay, so we have just found, given the number 512, we have just found, okay, what cell, okay, 15, 16, 15 being the x, 16 being the y coordinate, that particular cell maps to this natural number, okay? But this is just, a way of reversing the process, right? It's not a very good way to do it, okay? Because as I said, if I give you a really large number, then you're gonna need a very big spreadsheet to get to it, okay? Which means, the amount of time to figure out the inverse function is going to be not a constant time, okay? It's going to be linear to the value itself, okay? That is not nice, okay? If I can find a constant time way of doing it, it'll be much better. In other words, if I can just start with 512 and use all the usual math operator that we can perform using constant time. So addition is a constant time operation, subtraction is a constant time operation, squared is a constant time operation. Even something that is kind of difficult like square root is a constant time thing. Okay, taking the square root of 13 is not taking any more time than taking the square root of 6,000, for instance. Okay, so it's a constant time operation. So we now want to use those tools. Okay, those are the desirable tools that we want to use, but we have to figure out a way to express how do we get to this 15 and how do we get to this 16 given that we are dealing with 512. Okay, so that is our current task. Okay, now if you have read the module over the weekend, I mean, there's nothing surprising here, okay, because you already have seen how it is derived. So I'm just going to go through the notes here, just so that we can get an idea of how the concepts flow. And if you have any questions when you read through this particular module, if you have it written down anywhere, now would be a good time to ask when I get to that part and you go like, I'm not really quite sure how this works. Okay, now would be a good time to ask those questions. I have turned on MathBot on Discord, and that is why you can also use equations. If you know how to use LaTeX, you can now use equations in Discord. Okay, now the question is, but how do I use LaTeX? Okay, how do I learn LaTeX? With all the newer pages that I generate, if you right click on a particular equation, you can now say show math as, okay, copy the clipboard. Oh, okay, I see that LaTeX is still not an option here. I might have to change, yeah, it's still not showing up here. But LaTeX is not a, okay, I was about to say, use the word obscure. It is obscure from the perspective that it is not XML, it is not HTML, it is not Markdown, so it's not like anything that's modern, but it is not obscure from the perspective of how often is it used. Okay, it is used very, very often, and that's why Markdown also supports LaTeX. So you can actually look up LaTeX and get a quick tutorial of how to enter equations like this. This one is pretty easy because you really just type, for the most part, what you see here. The only tricky part is how do I get less than or equal to, which is \LE, and how do I get something over something? It is \frac, and then you use curly braces for the top part and then use curly braces for the bottom part. Okay, so there are documentations on the internet that can quickly get you acquainted with how to type something like this. I'll go ahead and do it in Discord. Okay, so kind of if you have Discord up, you can just go ahead and look at that. Well, while I'm typing, you cannot see the whole thing, but when I'm done, you get to see both the LaTeX representation and also how to put it into Discord. So I'm just gonna type this whole thing, W times W plus 1, the whole thing divided by 2. So if you want to enter any equations in Discord, once MathBot is turned on, you enclose what you want to type with double $signs. Okay, and then you press the enter key, and MathBot should automatically pick it up and render the actual equation like that. Oh, sorry about I have to apologize to Duck, okay, because he had typed something and I need to take a look. Oh, he's from another class. Never mind then. Now I have to apologize to this class because I just took some time away from this class to take a look at something else. Okay, so this is how you can type it in. Can you guys see the original equation? The part that says Dr. Tag A $, G something. Okay, and you can also see the rendering from MathBot, right? Okay, cool. So this is how you can learn LaTeX. You can use Discord to learn LaTeX now as a playground. So what I'll do, okay, don't play with this. in our channel. Okay, I'll give you guys a playground. Okay, so I'll give you a LaTeX playground. Okay, so I just added a new text channel, and I'll put this, I'm moving it right under the general channel within the text channels. So if you want to play with LaTeX, just go ahead and go to the LaTeX playground. And if you want to have a discussion of how to get something done, you can work with your peers over there. And I think it's useful in the long run, but it's not necessary for this class. Okay, in other words, if you refuse to learn LaTeX, it will not adversely affect your grade. Okay, but I think for those who are interested, okay, this can be useful in many different contexts. Because you might be able to use this in one of your math classes. Okay, if your math class has gone completely online using a remote modality, and you want to show your professor an equation and ask questions or to answer a question, LaTeX can be a really effective tool to help you communicate with your math professors. Okay. So that's just, a little bit of an extra thing for this class. I'm looking at the time. We still got some time here. Okay, so that's good. So I'm getting back to the text channel. And Aaron says, it as a dark mode background. Oh, the row thing. I have not set it up today, so I'm going to set it up now. So those of you who are watching this live, this will make it very easy. Let's see, where's my Discord? Okay, this is the Canvas page. So let me get back out and then leave student view, and then we'll go ahead and add that activity inside Olive Null. So add a quiz activity, making a new one. Call it row taking 2020-09-15, and move it inside the row taking group, which basically means it does not contribute anything to your actual grade. So just taking row taking does not affect your grade. All right, then we go into row taking and click edit. Set a deadline first. Okay, I have to turn off let student see the correct answer, and then we set up a due date, which is tomorrow, September 16th at 10:30 a.m., which is 24 hours since the beginning of this live lecture. Okay, there we go. And then we go to questions, add a new question. What is tax word for row taking on September 15th? And this is what I always, well, not always, but sometimes forget, is to change the type of the question. So if I forget to change this, it becomes a multiple choice, and there's only one choice, so it makes it super easy. So I have to remember to change this to a fill in the blank. Okay, there we go. And we'll say macros, M-A-C-R-O-S-S. That is the word of today. Does anyone understand why macros relates to what we talk about today? Okay, I will show you a screenshot next. Okay, so update the question, but that is the answer. Okay, macros, M-A-C-R-O-S-S, all lowercase, is the word for let me publish it first, because otherwise you guys won't enter it. It's not macros, it is macross. M-A-C-R-O-S-S, cross. Okay, so macross has significance probably to your parents. It's an anime series. Okay, so let me go look for it. Macross space.
I knew the reference, I just didn't think it would be that.
It'll be what?
The anime series. I thought it was going to be something computer science related that I didn't know.
Oh, I'm a big fan of anime as well. So I'm gonna put this in today's text channel as you know it relates and it doesn't relate to what we are talking about, but there we go. Now do you see the relevance? Barely. The Macross is a gigantic spaceship and is capable of folding space so that it can travel a vast amount of distance, in a very short amount of time. And also this relates to the first picture that I included in today's lecture, okay, which is a picture that explains what is a wormhole. So in that picture, okay, it is projecting our quote-unquote three-dimensional space as if it is a two-dimensional space. So that little connection, is through a dimension that does not exist or we cannot perceive in a three-dimensional space. That is interesting because that's what G inverse is doing. Okay, so let me go back to the notes of today because I think everything is really kind of coming together in a very, 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 very strange way. Because when you look at G inverse, I'm fast forwarding a little bit here because I do want to associate the relevance first. Okay, so what G inverse is doing, oh darn it, I don't have that here. Okay, I just don't have it explicitly stated, so I'll put it in the whiteboard. Okay, so in the whiteboard, let me go get the editor of the whiteboard. There we go. So in the whiteboard, what I'm typing here is the description of G inverse as a function. Okay, so G inverse, okay, as a function. So what you're seeing here, this is LaTeX already. Okay, before I type the last $sign to say this is the end of the entire formula, what you're seeing is basically what I have to type in order to describe what I want to describe. So G inverse is a function. The domain of G inverse is the set of all natural numbers. So if you want to type it, it's math BBN. Okay, that's the funny looking n that we see. Okay, this is our domain. Okay, this is where we map elements from. Okay, and then we have the single line right arrow. Okay, which is a notation separating the domain from the codomain. So now we want to describe the codomain. So when I describe the codomain, I'm going to put in extra parentheses just to emphasize that treat this entire thing, this entire set, as the codomain. Okay, and the codomain in this case is n times n. Okay, so I'm using times, backslash times to give me the what looks like a lowercase x, the usual times symbol. Okay, and then math BBN again. Okay, and then close paren is already here, and I just need to use a $sign to close the entire thing. Oh, okay, the focus is on the wrong window. There we go. All right, so this is G inverse. So G inverse is basically mapping a smaller dimension, okay, I shouldn't say smaller dimension, but a space that has one fewer dimensionality, okay, one less dimension, to a space that has one more dimension. That is the job of G inverse. Okay, it goes from a linear space in this case to a plane. Okay, is that okay? Does everybody understand what I'm talking about? Yes? No? Okay. Yes. Okay. Excellent. So that's the job of G inverse, which means in the context of space folding, this gives us the ability to go from a space of lower dimension to a space of a higher dimension. So once you get to the space of higher dimension, you can cross distances more easily. Now let me show you, what I mean by that using the example that we have here. Okay, this spreadsheet, crazy spreadsheet, right? So if you look at the distance between, say, 31, okay, let me highlight it using a different color. So this way, I'm basically illustrating between which two things we are talking about. Okay, so we'll use a light blue shade for this one. And let's just say that, this is the other one, okay, 392 as a linear value, or in 2-dimension, 1314, okay? So we'll go here and change its color as well. Okay, so we'll go to this, and we'll change it to slightly green. There we go. Okay, so let's just say that, 1 is our, where we start, okay? Let's say 31 is our point of origin, and 1314 or 392 is our destination. This is where we want to go. When we look at this from a linear space perspective, okay, as just natural number, they are a long way out, aren't they? Because you have to go from 31 to 32, 32 to 33, 34, 33 to 34, and so on until you get to 392. So if you are a being on that's in that space, just natural numbers, the distance between where you are and where you want to be would be 392 minus 31. So the distance that you have to travel is going to be what? 361, okay? So you have 361 units to travel before you can get to the destination. Sorry, I just typed something on the keyboard. Okay, Control Z, undo. Okay, there we go. So you have 331 units to travel before you can get to the destination. On the other hand, once we map into the 2-dimensional space, the actual distance between these 2 points is not quite that bad, right? Because you can say from here I can travel, to here, and then from here I can travel to here. So let's do some counting here, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, so instead of having to travel 331 units, we only have to travel, what, 12 or 11? I cannot remember. So, but it's a big difference, okay? That is the whole idea of, in a lot of science fiction, of folding space, because we are thinking about our 3-dimensional space as a subset of a higher dimensional space. So the way our 3-dimensional space is like in a higher dimension, we just warp it, okay? We just kind of fold it, okay? And therefore the picture at the very beginning of the text channel. So we are folding it, okay? We are wrapping it around, and then we just go like, hey, now we can see that this point is really right across from that point, and go like, psst, connect them, okay? So that is why I use the word macros as today's word of rotating, because that is sort of what what science fiction is using space folding for, is to turn a lower dimension distance, which is really long and there's a long way to go, into a much shorter distance in a higher dimension, okay? And that's why, okay? But I think the choice of that word is also to help emphasize what we are doing in today's class. If I want to make it even, I'm trying to insert an arrow to go from here to here, and it does not look like I can do it in Google Sheet. Okay, I'll research that later, but it's not that important. But if you were to imagine a straight line going from here to here, that line would have been a lot shorter compared to having to go through all the diagonal lines. Okay, I have to pick the right one. Okay, so into here, 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 here. So you can kind of see that if you have to scan all the diagonal lines before you get here, which is the distance in the linear space, that is a lot longer compared to having to just go from here to here in a higher dimensional space. Okay, so that pretty much concludes today's lecture, because we are out of time. Okay, so I didn't quite get to relations, but please read ahead of me. Okay, first of all, review what we have done today. Okay, next time I'll go ahead and explain the rationale of the rest of this space folding business, and then we're going to move on to relations. So I'm almost 100% sure that we will get to relations on Thursday. So read ahead of me, because that will give you a better way of understanding the content when we get to Thursday. All right, so I got a few people typing, and let me scroll back down here. Oh, okay, that's the share folder is a link in Canvas. So if you go to Canvas and go to the modules, the first module at the very top of the home page has that share folder link. But to access the content, you probably have to sign in to Los Rios first, which is what you have to do to get into Canvas anyway. So I don't think you would have any problem accessing the share folder. Oh, Alex, that is a very, very good question. We can now fold a 3D space into 2D space. Why? Because we look at the 3D space as a 2D space plus one extra axis, right? The 2D space can fold into 1D space. So now we have the 1D space that used to be a 2D space combined with the independent 1D space. Now we have a 2D space again. In other words, you can nest the application of G to fold a 3-dimensional space into 2-dimensional space, and then from a 2-dimensional space you can fold into 1-dimensional space. So this is really good. Okay, I'm glad that Alex proposed this, because now we can fold any dimension, any fixed number dimension, into one single dimension. Yes, so that is exactly what we are dealing with here. So that picture is good, Alex. But let me just in general describe how to look at a 3-dimensional space and how to fold it. Okay, so you can basically look at a nested application of G. Okay, so let's say we have X, Y, and Z as the 3 axes. Okay, given a voxel. Okay, it's not a pixel anymore, it's a voxel for volume element instead of a picture element. So let's say we have a voxel that has X, Y, and Z in it. So you can apply nested, G, X, Y to combine the X and the Y into one single natural number. Then you combine that natural number with the Z axis. So that turns into one single natural number. So we'll just call this N. Okay. So this is how we can fold a 3-dimensional space into 1-dimensional space, is by nesting G within G itself. So yes, so I'm glad you mentioned that, Alex, because this is the how should I put it? This is kind of like the corollary of what we have talked about today. Is if I can fold 2 into 1, then I can fold 3 into 2, and then 2 into 1. Then I can fold 4 to 3. Actually, 4 is a special one, because if you want it to be easy with a 4-dimensional space, you fold the first 2 dimensions into 1, then you fold the other 2 into 1, then you fold the 2 resulting linear space into one single linear space. So you technically only need to fold twice, so to speak, but there are actually 3 folding action. Let me I'll put this in, and then we'll end today's lecture. So if you look at the whiteboard, if you have a 4-dimensional coordinate, which is WXYZ, then we can apply G to WX first, then we apply G to XY, and then we take the result of G of WX, and then we take the result of G of YZ, and then we fold it one more time, and we call that N also. And oh, okay, I see why it's not turning into what I think it should turn into. There we go. It's still missing a $sign. It has one too many $signs, that's why. There we go. So this is how we can fold a 4-dimensional space into 1-dimensional space, or one way to do it. Okay, but no matter how you do it, you have 3 G's. Okay, the only question is how do you distribute those 3 G's, and there are several ways to do it. All right, so Alex says this sounds so nested in math concepts that it can't be related to reality anymore. I don't know about that. As I said, I only have some knowledge, okay, because of teaching this class. in a countable space, which is basically the set of all natural numbers. But if you look into string theory, okay, so string theory is saying our reality, what we perceive as our reality, is a membrane, okay, it's a surface in a much higher dimensional existence. So I cannot remember the dimensionality of the space that string theory deals with, but it is in the order of I cannot remember, but I think it's in the order of 10. Okay, so we're talking about a 10-dimensional space in which we are nothing more than just a thin membrane or a wire, what is equivalent to what we see as a wire in a 3-dimensional space. So so fascinating stuff. Okay, fascinating stuff. But Alex, I'm kind of glad that you're interested in this. You might want to get into theoretical physics, or just take one or two classes when you get a chance at a 4-year university, because that aligns with what you just said. But to the rest of the class, the class lecture is over. Well, learning is a lifelong process, so there's no need to say that I'm not at an age where most people go to college, because these days we have Wikipedia, we have YouTube, and so on. So it is a lifelong process, and it doesn't cost you much either, except for time. Yep. All right, cool. So I'm going to officially call this the end of today's lecture. No homework yet, okay? So I will try to kind of think of a homework for you guys to do. But one thing you can do, sort of as an activity, not so much as a homework, is to go back to this spreadsheet and really understand how it works, okay? One, it might teach you a few things about what, kind of simple things that you can do in the spreadsheet. But two, this really gives you a visual context of the Aleph Node chapter, or a good portion of the Aleph Node chapter, and it also gives you an idea of what is equivalency between the cardinality of the sets. Okay, it gives you a very kind of visual and pictorial way to understand all of those topics. All right, so with that, I am going to close today's live stream, but I will be online for a while because I have office hour from noon to 1. And then I will be online in a meeting from 1:15 on to whenever the meeting ends. So I'll be kind of online, but I may or may not be able to answer questions, after 1 o'clock, depending on what kind of free time I have. Cool. So I'll see you guys on Thursday, and have a good day.